stimulated emission. Here we have two energy levels in an atom, E2 and E1. E1 is the lower of the two energy states. And say I have we're calling these a transition. This is a transition between the two states. And when we're talking about a transition, we're talking about the atom itself losing energy or the electron jumping down an energy level is two ways that we can see it. Now, this transition will result in what? A photon. How much energy will that photon have? It's a little photon. Imagine it as a particle at this point. Its E is equal to HF, which is equal to E2 minus E1, which we're going to call change in energy. Okay, that's all true for that photon. If I take E1 from E2, that leaves me with delta E, which is the change in energy, and it's equal to this discrete energy jump here, this discrete transition. And the photon has that energy also by the conservation of energy. We call this spontaneous emission. How has this come about? Because I've sent in a photon of energy delta E and caused a transition from the lower state to the higher state. Has to be, doesn't it? It's the only way that it's going to happen. Oh, well, unless, of course, the atom itself was in an even higher energy state and it was jumping down step by step. But say I cause this transition here. So how long does this take? I shine light on this atom. I excite it and it jumps back down. How long do you think this takes? Not long at all. It's good. That's true. It takes around about 10 to the power of minus 8 seconds. Yeah, we can't tell. Okay, as far as we're concerned, we shine light on it and then it emits light instantaneously. Okay. Okay. That's spontaneous emission. What if we had, now this is a different atom, and so what I'll do is, to denote that it's a different atom, I'll draw the energy levels closer together, slightly. And what if that atom was already in an excited state, and then we shine some light on it? And I'll call this E4 and this E3, just to say that these are different energy levels in a different atom. If I shine light on that atom in that state and I give it sufficient energy, delta E in this case here, I can induce that atom not to go up an energy level, to also transition down an energy level. What do you think it emits in order to do this transition, to make this transition? Well, it was already excited and I sent in that energy again, exactly the same as the transition that it's taken. What's that, Matthew? No, think about it. I'm sending energy in. It's already in an excited state. When that energy strikes the atom, it jumps down. Yep. Well, we call this something. It emits, just emits 2 photons of equal energy, delta E each. Okay? Okay, delta E is equal to E4 minus E3. Change in energy. So the total energy out here, total energy emitted equals 2 times delta E. Okay? Remember that this is a very specific transition in a very specific atom. Doesn't happen with all atoms. Happens with very, very specific few, and physicists in the well, actually, I don't know. The application came about in the 1950s, thereabouts. But they worked this out, and because of this, they were able to come up with the idea of this, light amplification by stimulated emission of radiation, or just LASER. Laser. Okay, so they sent some light in. This atom was already in its excited state for some reason, and it sent out twice the amount of light, which was in phase. They were in phase, and they were exactly the same wavelength, monochromatic light. Okay, this is where the lasers application comes in. We call this stimulated emission. We have stimulated this atom to emit radiation. And I wrote this in a different color here. This photon has stimulated this atom, which was in an excited state, to drop to a lower energy state. This is useful in the application of lasers. Not all atoms do this. But am I right to move down there? If I draw exactly what I drew before, draw another stimulated emission, but then very close by, because we very rarely have just one atom. We often have trillions of them. There's another atom close by, and I'm going to draw these transition. So imagine we get a stimulated emission there. What happens over here? So this atom, already in its excited state, a photon comes in, excites it, causes it to emit 2 photons. Then another atom is very close by. One of those photons goes on to stimulate that one to emit 2 photons. What have we got? We've got an amplification going on, haven't we? All right. So all of these atoms in these excited states are being excited by 1 photon and emitting 2 photons. We get very quickly an amplification of that very specific frequency of light. If I can cause that to bounce around and reflect inside this area where we contain this gas, because a laser is just a tube full of gas with mirrors on the outside, essentially. If I can cause this gas to keep doing this and bounce around, eventually what happens is we can allow it to come out through a very small hole in the side where there's no mirror, or a kind of a bit of a mirror, and eventually we have a nice laser light. Okay, so which is monochromatic and coherent. The most common laser that we use in schools is a helium neon laser, HENE laser, 632.8 nanometers. They know this wave. I think that's right. They know this wavelength pretty well. Why do you think we have the 2 gases there? One of those gases obviously has this state where it, and this property of itself where it has this excited state, and by stimulated emission it can amplify the light. But the other gas, maybe, what do you think? What function do you think the other gas has? Because all we do is we have a laser, what is called a laser cavity with these 2 gases in it, in certain proportions rather, and we pass an electrical current across that tube. Normally what that does is causes if you have a discharge tube, then it causes the gas inside to light up if you give it a high enough voltage. One of these 2 gases has a very specific energy jump that allows one of the other gases to get to this state in the first place. Okay? This state here is called a metastable state. And in order for the atom in the first place to go from its ground state, because if you've just got a cold cylinder of helium and neon, none of it is in a metastable state. It has to be put into that metastable state in the first place. We pass an electrical potential difference across that tube. We cause one of these atoms to get excited. When it gets excited, it emits a very specific frequency photon, which allows the other gas to get to this excited state, which is a metastable state, and stimulated emission starts to occur. Metastable means that it's generally reasonably long-lived, and I think we're talking 10 to the minus 6 or 10 to the minus 7 seconds. So long-lived, still very short-lived in our macro world, in our idea. Okay? So metastable state, long-lasting. Relatively long-lasting. Last thing, population inversion. Does anybody know what this is? Population's talking about the excited gas, population of atoms. It's just simply more atoms in the excited metastable state than atoms in the lower state. Lower state. Now, why is population inversion something that a phenomenon? We need this to happen in order for lasing to occur, for this thing to happen. We need more of these atoms in this metastable state. Otherwise, what happens is the chain reaction kind of breaks down and we don't get a laser. If we get this population inversion to occur, they're all excited and they're all getting more and more excited, and they're all like by stimulated emission amplifying this light, and we get lasing to occur. Okay. If anybody had done their homework, they would know that. Yeah. I'm looking at everybody. Here's your homework for soon. I know there's a test coming up. Watch Laser's video. I'll be watching to see who's watching.